So, in the context of function approximation, right, so we have been talking about this function phi, right. This is some representation of the states and actions, and we talked about how this can be done in a grid world setting here, or how it can be done in a kind of object manipulation task and or something like that that we looked at earlier, right. So, both of these we saw how features can be designed. So, now I am going to talk about a couple of different things with regard to this defining this phi vector, right. So, we have been looking at how the phi vector can be designed for a variety of things, right. I want to tell you something else, right. So, we all remember the lookup table, right. In a lookup table, we basically had one entry for each value that you wanted to represent, right. So, that's the way that we were handling it, one entry for each value that we wanted to represent. And so, you had your lookup table, let us say, let us talk about the manufacturing problem, right. So, where you had you can either advertise a product or not, and then you can manufacture some things and so on and so forth, right. So, or do research for a product, right. So, in that case what we had two states, right, hot and cold. Let me write it out in a slightly different manner. So, you had two states, hot and cold. Then you had two actions, A1 and A2, where A1 for hot was advertise or not advertise, right. So, this was Q of hot comma advertise, and this will be Q of hot comma not advertise. These are the two actions you had in state hot, and likewise this was Q of cold comma say research, this is Q of cold comma not research, right. So, basically you only had 4 Q values that you had to represent in the lookup table, right. So, now what we will do is we will define our features phi in such a way that this lookup table can be captured in a linear function approximator. So, how would we do that? So, I am going to say my phi of hot comma advertise is equal to 1 0 0 0, right. Phi of hot comma not advertise equal to 0 1 0 0, right. And phi of cold comma research equal to 0 0 1 0. Phi of cold comma don't do research equal to 0 0 0 1, right. So, these are my 4 vectors that I have defined for my representation. So, now once you have this phi, let us write the Q function, okay. So, you have Q, right, Q of S comma A, right. So, that is going to be equal to W1 times phi 1 of S comma A plus W2 times phi 2 of S comma A plus W3 times phi 3 of S comma A plus W4 times phi 4 of S comma A, okay. So, this is going to be, so what is phi 1? So, in this case it's 1 0 0 0, right, and see phi, so sorry, phi 1 is right this one, right, that is phi 1, that is phi 2, that is phi 3, that is phi 4, right. So, for each one of these it is going to be like this, right. So, let us look at what will be Q of hot comma advertise, right. So, Q of hot comma advertise will be W1 times phi 1 of hot comma advertise, right, plus W2 into phi 2 of hot comma advertise plus W3 phi 3 W4 phi 4, okay. Now, let us fill in what this phi 1, phi 2, phi 3, phi 4 is, right. So, the phi 1 of hot comma advertise is 1. So, I will write 1, right. Then phi 2 of hot comma advertise is 0, and phi 3 is again 0, right. Phi 4 is again 0. So, this is equal to W1, right. So, if I am going to learn, I want to learn, make sure that my W1 converges to Q of hot comma advertise, and likewise my W2 will go to, right, you can see that this is the only one that has W2 as 1, right, it will go to the Q value of hot comma not advertise, and W3 will go to the Q value of cold comma research, and W4 will go to the Q value of cold comma don't do research, right. So, for each one of these entries that I wanted, right, so Q hot, each one of these 4 entries I wanted, so this will be W1, this will be W2, this will be W3, and that will be W4, okay. So, that is what I will end up with, right. So, these are the values, and to achieve this kind of an encoding of the lookup table in a linear function approximator, I will choose my feature representation to be of this form, okay. Make sense? Good. So, now you understand how this feature encoding works, right. So, I can actually, even lookup table is a form of linear function approximator. I can use I can use function approximators, right. So, I can use function approximators that are not necessarily, linear, right, in the feature vectors, right. So, this is essentially what my phi is. This is my phi 1, phi 2, phi 3, phi 4, phi 5 of S comma A, right, and that is phi 6 of S comma A. So, these need not necessarily be linear in the basic description of S and A, right. I can use some kind of a basis expansion, as you would have seen in linear regression earlier, right. So, likewise I can do that, but finally the function that I am solving will be linear in the W's. That is the only requirement I have. So, as you can see that once I have actually looked into the state J and action north, I would basically get a function that looks like this, right, and I have to now solve this for all possible states, and I solve that using some kind of a regression problem, right? And we talked about all of this. How do you solve this with the TD target and all that? So, now it turns out that you don't really have to use features like this. You can use all kinds of crazy made up features like this phi 1, phi 2, phi 3, phi 4 to simulate a lookup table also, right. And we will see in the next slide how I can do slightly more powerful things than the lookup table, right. But before we go on, I just had one other point that I wanted to make, right. So far we have been talking about how we will have your phi, right, as a function of states and actions, right, and then you will use phi transpose W to get your Q function, right. There is another way you can do this, right. So, instead of thinking of a function approximator, right, this parameterized by W, taking its input S and A and giving you as an output Q of S comma A, right. So, that is one way of thinking about it. Another way of thinking about it is to say that no, I am going to have multiple W's, each one of them takes the state, right, and gives us output Q of S comma A1, Q of S comma A2 dot Q of S comma AM, right. There are M actions. So, this will be W1, W2, Wn, right. These are all vectors, right. W1 is a vector of weights or whatever, like a matrix of weights or what sort of thing. But if you are talking about linear function approximators, W1 would be a vector, and this will be the output, right. So, there are basically, if there are M actions, there will be M such function approximators or regressors, and this totally will give you this same function as you have here, right. So, feeding A as an input, you are basically conditioning A on the output, right. So, if you think of this, so your phi of S comma A1 will be equal to W1, right. So, it's something like this, right, whatever phi of S comma A1 is the vector that feeds into W1, right. Right, phi of S comma A1 is a vector that feeds into W1, so on and so forth, right. So, one advantage of doing this is now I can just think of phi of S, right, because that is the one that gets fed into the linear regression. So, I do not have to worry about adding features for the action A, and depending on whether I need different features for different action, right, I could use so I could use a phi 1 of S going here, phi 1 of S, phi 2 of S going here, and so on and so forth. But typically, so what happens, as you saw in this example that we had, right, so the states were independent, right, and the action feature was independent of the states, right. The state features were independent of the actions, right. We had xs, ys, xs squared, ys squared, xs, ys, and then finally you had a separate encoding for the action. Typically that is what will happen, right. So you will have the same set of features will be used, and but you will use different weights for different action. So that's one way of handling it. Of course, other ways of to do this, right, and a third way, like we were just saying, is to say that I am going to have W1, W2 all the way to Wn, right, and I am going to have S independently feeding in. So this will be phi1 of S, this will be phi2 of S, phi k, phi m of S, right, and the output will be Q. So there are multiple ways in which you can do this, right. You can just feed in the state and action into a single function approximator and have it output the state and action. So for this you need to have some way of encoding the action into a form that is numerically computable. But if I don't want to do that, right, if I don't want to make the action into a number, right, if I want to just keep it as left, right, up, down, then I can use this kind of a formulation, right. So where I just have these actions as specific outputs, and I have k actions or m actions, those come out as m, right. And likewise I could have a different function approximator, where instead of using a single representation for the features, I use a different representation for the states depending on which action I am doing the computation for, right. So there are all of these are possible solutions, and as you will see, when we have more complex function approximators as we go along, many of these functions, these phi's, will actually be learned, right. You don't have to write down the phi's like we have done here, right. We don't have to explicitly write down what the phi's are, okay. So these are all kind of things to keep in mind while you are designing what is the function approximator that we will use for solving the problem, right. So while you are designing the function approximator, these are all things to keep in mind, right. So let us look at a simple thing, right. So one powerful, actually powerful function approximation method, right, is to say that we will do some form of state aggregation, right. Some form of state aggregation. So we already looked at the state aggregation, where when we said that we are going to take a 2 by 2 workspace in which a robot can move and then put a grid, right, and then we are going to say each cell in the grid, right, is a state, as opposed to giving the xy coordinate, we put a grid and then we used a grid world, right. So that grid world is in some sense a state aggregation, because every cell in the grid, right, every cell actually corresponds to multiple xy coordinates in the cell, right. So the idea here is we are assuming that within the cell, right, within the cell, because the xy values change a small bit, within the cell there would not be too much of a change in the q function or in the v function, right. So within the grid, right, so I have this xy coordinates, right, and then I am going to make this grid, right. So I am going to make this grid, and I am going to assume that within this grid, right, whatever states are there, they are going to have the same q value, and they will not change by a whole lot. So that is the assumption that we make here, right. Is it a valid assumption? In many circumstances, yes, it is a valid assumption. And how will I encode this, right? So I am going to have as many components, vectors in my phi as there are cells here. So there are 25 cells here. So I will have phi1 to phi 25, right, and phi1 of S will be equal to 1 if S belongs to cell 1, right. Right, so I can number the cells 1, 2, 3, 4, 5, 6, 7, 8 all the way up till 25. So if I say phi1 of S will be 1 if S belongs to cell 1, that is if the x coordinate of the state, right, if xs is lesser than this value, right, and ys is lesser than this value, and x is greater than y is greater than 0 and x is greater than 0, then S belongs to cell 1, right. Then phi1 will be 1 equal to 0 otherwise, right. So this is how I will encode it. So earlier what did we do? For every state action pair that we wanted to consider, right, so we will keep 1, right. So for if this is this particular state action pair, then the value will be 1. Like that, if this is this particular cell, then the value will be 1, otherwise it will be 0. Now, if you have a cell and action combination, so instead of having 25 fees, you will have 25 cross 4, right, 100 fees, and for every state action combination, you will have, so phi 1 will be 1 if the state is in cell 1 and the action is 1, right, and phi 2 will be 1 if the state is in cell 1 and the action is 2, like that, right. So, we would probably define a set of fees like that. So, is that clear? So, just generalizing the lookup table instance here. So, here I am kind of using the one encoding for each state idea, right. So, I am kind of using this instead of this setup, I am kind of assuming you have this setup, right. So, you just use the encoding for the phi once and then you give the actions. You do not have to code the action as 0 or 1 or anything, right. So, that is basically what we assume you are doing, right. So, this is the simplest form of state aggregation. We already looked at it and it works pretty well, right. So, so that is what we are talking about here. The naive method is to say that you divide the grid into a smaller 10 by 10 grid, and but the problem is that that when I go from cell 1 to cell 2, right, even though, let us take a close up look, right, let us take a close up look. So, this is cell 1, this is cell 2. So, 2 states here and here, right, in cell 1, I am going to change the color, right. Let us say 2 states here and here in cell 1 will have the same value, right, but 2 states like this, right, which are much closer to each other, right, they are much closer to each other than these 2 states, right, but they will have a different value, and that could potentially be a big change in the value between these 2 states, even though they are likely to have the same value by our argument, right. States that are close together should have the same value. So, by that argument, these 2 should have the same value, right, but because of the way we have done the discretization, they could have a very different value, while these states which are far away, in fact this and this also, right, which is much far away, will still have the same value, right. So, this is basically looking closer into that 1 2 thing. Right. So, how do we change that, right? So, the idea is to use something called coarse coding, right. The idea is to use something called coarse coding. So, what does coarse coding do? Coarse coding, instead of doing this kind of disjoint discretization of the state space, right. So, what have we done here? We have done a disjoint discretization, right. So, we have just divided this into cells, and cell 1 and cell 2 do not have any overlap, right, they are disjoint, right. So, a state can either belong to cell 1 or will belong to cell 2. So, instead of doing that, you have this kind of a discretization. Here we are showing, instead of square cells or rectangular cells, we are showing circles, and you can see that the circles have a lot of overlap, right. So, if you pick any one state, right, like this x here, right, it is now in the intersection of 3 different circles. So, and the same thing, same feature encoding we will have, right. So, phi 1 of S will be equal to 1 if S belongs to circle 1, right. But now the problem is multiple F's, multiple phis will become 1, not the problem. The advantage is that multiple phis will become 1 for a particular S. For example, take this, right. So, there will be 3 phis, right, some phis, right, we do not know what it is, right, it is phi I, phi j and phi k corresponding to circle I, j and k, right. 3 of them will be 1 for the state x. So, now what will happen? So, my value, right, my q or right, let us say my v of S, right, will be wi plus wj plus wk, right. It will be the sum of 3 things. So, when you move from here to here, right, so there is no abrupt change even though I have crossed a boundary, right. So, in this particular case it will be the sum of wi and wj, in this particular case it will be the sum of wi, wj, wk, right. So, basically you are getting one more, so the kth circle getting added, right, this is the kth circle that is getting added now to the features, right. And likewise if you move from here to here, then the ith circle will get dropped, right, this is I, let us say this is j, that is k. So, while this dot will have wi plus wj as the value, this dot will have wi, wj, wk as the value, and then if you go here it will be wi and wk, so on and so forth. So, it is not like you will have a huge step change, and there will be some transfer of values, right, for nearby cells, right. So, only if you move pretty far away will that be no generalization, right. So, that is the advantage of doing this kind of a coarse coding, right. So, what is the problem with coarse coding? So what's the problem with coarse coding? So I hope people understood what I meant by saying there will be phi 1, phi j, phi k, phi I, phi j, phi k, all three will be 1, right, for this, right, because there are 3 different circles, right. I said if phi I of S equal to 1 if S belongs to circle 1, and likewise since it belongs to circle I, circle j and circle k, there will be 3 phi's that will be 1, okay. So the problem with this kind of coarse coding is that, see for example in state X that we were looking at so far, right, there are 3 phi's that will come 1, right, but for state Y that is out here, right, state Y out here there will be only 2 phi's that turn on, right, not 3, right, and then for some state out here, right, there will be just 1 phi that turns on, not 3, right. So the number of weights that contribute to the value of a particular state is not constant, and it varies over the state space. So some states can have a better representation of the value than some other state. So if we come up with a systematic way to cover the state space so that each state gets an equal number of phi's representing that state, right, then you can have a more uniform fidelity for that. And so there is a specific form of this coarse coding called tile coding, right. That's very popular. It used to be very popular. It turns out to be a fairly powerful function approximator even today, right, and it can be trained with a lot less data than you would need for some heavy duty neural network training. So as long as you have a simple enough state space on which you are trying to solve, right, using RL, you might want to consider tile coding as your method of choice as well, right. So the idea behind tile coding is the following. So there are 3 different colors here. I'm not sure if you can see it, so let me just draw it out in right. That is one set of, let me draw the yeah. So the green is the actual state space, right. This is the locations over which the robot can move, right, or the agent can move. The green is the location over which the agent can move, right, and the red is one set of discretization, right, and the blue is another set of discretization. So what do we mean by discretization? It's something like this, right. So I'm going to divide it up and I'm going to have like 25 phi's that represent one location in the cell. So remember this green is my actual world, right. So if I take any point, right, if I take any point in that world, right, so I take any point in that world, so this green point in the world, now it is going to appear like just like here, right, just like in the original case. So if I take a point, it is going to appear in a specific cell, right. So likewise for the red grid, the green point will appear in one cell, and for the blue grid, the green point will appear in one cell, some cell, right, we are not telling you which one, right. So if when I am here, so it is going to appear in some cell in the red and some cell in blue, right, and then if it moves here, right, so let us say it moves here. So what has happened is on the red box, right, it's moved here, right, on the red box it has moved out of the tile, that's the red box, it has moved out of that tile, right. So it just basically went from here to here, something like that, right. On the other hand, in the blue box, right, it is still within the same tile. So it is not like it's completely lost some generalization between these two states, right. And the nice thing about it is, if you notice that the green is contained within both the blue and the red cells. So that means that every state in that green area will have one cell in red and one cell in blue right up, every state. So there will be 2 vectors, 2 components of your vectors phi, right. So let us say that red is phi 1 to phi 25 and blue is phi 26 to phi 50, right. So in phi 1 to phi 25 there will be 1 1, and phi 26 to phi 50 there will be 1 1, right, for every state in the green area. So now I could do this in multiple ways. I can just have blue and red, just 2 tilings, but I could have 10 tilings also if I want. So 10 different grids, and so that means that for every state we'll have 10 points that will light up, right? So 10 features that will light up. So so for each tiling that you use, right, so you will get one feature on, right. So how do I make sure that I get these different tilings? So actually you don't do too much thinking about it. If you try to make the tilings equally spaced, right, so I start off at 0, then the next one is going to be at 0.5, the next one is going to be at 1, and the next one is going to be at 1.5, and so on and so forth. It turns out that's not a great idea in practice, because the generalization doesn't really work very well, right. So what actually works well is, suppose let's say you have a 2D space, right, and so take some random displacement along the x-axis and some random displacement along the y-axis to go from one tiling to the next tiling, right, and that works the best in practice. Okay. So that's it for tile coding. And tile coding with some more clever implementation tricks and so on and so forth gave rise to a function approximator called CMAC, right. And for a long time, CMACs were the most popular function approximators for reinforcement learning. It stands for cerebellar modeled actuation or articulation controller, right. So it's basically inspired by the cerebellum in the brain, and so they look like there are all these overlapping kind of activation functions in the brain, in the cerebellum. So they actually talked about this as a cerebellar modeled articulation or actuation controller, and so that's basically the architecture that was popular for a long time for reinforcement learning, and still quite a fairly powerful classifier. First big advantage is linear, right, and the second big advantage is that when I am really looking to see what should be the value function, right, I don't have to do any any real products, right. As soon as I figure out what cell the state lies in, I just pull out the corresponding weights and then add them up, right. There is no complicated forward pass like you have in a neural network, right. You just find out which cell they occur in, and if you have a rapid way of computing that, right, so once it tells you which are the indices of the cells, you just add the weights and you have your value function. Okay, so that's a big advantage with CMAC. So the forward pass is very easy, and the backward pass is also easy, because you will be updating in every backward pass only the number of weights as there are tilings, right. If there are 3 tilings, then you will update only 3 weights. You don't have to touch the rest of the weights when you are updating the network, right, in the backward pass, right. And there is no real backward pass, it's a linear, right. So you could use gradient updates as we saw earlier, but the gradient update just becomes the phi function, and the phi in this case is either 0 or 1, so it's all easy. So you just use the TD error and the weights that were activated, right, basically the weights corresponding to the phis that were 1, and then you change it by delta alpha times the TD error. So that's basically the update. So the forward and backward passes are very easy when you are doing this kind of tile coding or coarse coding approaches, and therefore they are lightweight, easy to use function approximators, right. Cool. So far, yeah, of course, just a passing note, right. All of you know this, but just reminding you, right. So what we are doing here, right, is some form of stochastic gradient descent. So why is it stochastic gradient descent? So remember, the true gradient at a setting for the parameters theta, the true gradient is computed by taking the expectation over the data distribution. So I have to look at all possible ways in which the the trajectories can evolve for a particular setting of theta, right. So I have to sample multiple times from the value function and look at and also sample multiple transitions and get multiple rewards, and then I have to take this average, right, or actually I have to truly compute the expectation. Since I am not able to do that, right, and I am basically taking a single step, and based on that I am doing my update, right, this is going to be a stochastic gradient descent, right. So all of you know that. So the gradient is not, even though we keep saying this is the gradient, it's not being exactly computed because we are not taking the expected value, right. So it's a stochastic gradient descent, and in fact we typically end up doing mini batch when we are doing gradient descent. We'll see in a bit, right. We actually do mini batch gradient descent, right, and even with mini batch gradient descent, it is still only an approximation of the gradient, right, and therefore it is still SGD, right. It allows for smoother convergence, right, and in fact it allows for much better estimate of the gradient. Sometimes you get arbitrarily close to the true gradient, but since it's not guaranteed always, so it's still a stochastic gradient descent. It's not true gradient descent, but it's okay, right? So we all know stochastic gradient descent is fine. It will all converge at the end of the day. But this, just keep this in mind, because I'll refer to this later when we talk about deep learning, right?